Okay, in here, so let's look at the center of gravity of an arc. So the main difference between an arc and a sector is, an arc is something like just a rod which is bent in the shape. We don't have any mass in this interior section. But when it's come to an arc, when it comes to a sector, it is actually a plate. We have mass distributed in this section. So when it comes to that, I'll just discuss it. So you should understand, if you just take a rod, it is consists of infinite number of rod alignments. So when you just have small rods, tiny rods of negligible mass dm, infinite collection of them can produce this rod. So why we are just going for this infinite scene is, you can see there's a bent nature. So when you're able to cut them small, it will be almost a straight rod. There will be a slant curve in nature. So when you add all of them, this nice curve can be produced. That's the reason why we are just going for this negligible portion in every center of gravity videos. If you look at a cone, we were just considering it as, for a solid cone, we were considering tiny coins. For a hollow cone, we were considering tiny rings. So each and every time it's compared to a relatable geometry. So if you look at here, we are comparing this with a relatable geometry for a tiny rod. So which is almost in straight. So we must know the length of the rod to find the mass. Let's say the density of the rod is uniform. It is, now we are having density, surface density and linear density. So when you are just obtaining the length, we must consider linear density. For example, let's say at an angle theta, there is a rod. There's a certain point. And after a small distance, let's say d theta, the other end of the rod is present. One end, the other end. So it's actually tiny. For a better view, I have just zoomed it. So this is going to be the actual length of the rod. You know that each and every point where you touch the end of this arc, it's every time the radius of the arc. It never changes. Only thing which is going to vary is the angle which you are just subjecting. Let's say in here it was 30, maybe here it will be 60. So every time the angle is the one which is varying. So the length of the rod would be a times of d theta, because this is, the radius is a and an angle of d theta. So this part will be a times of d theta, which is the length of the tiny rod. So in here we have considered the length. I think in the other questions we were considering area. We had mass per unit area. So we can actually find the negligible mass, because when you multiply it, we know the mass of that. When we are just considering a volume, we multiplied with the density. So volume times density gets you the mass. And we assume that the density is uniform. Similarly, in here we assume that, okay, there is a uniform density throughout. And since we have considered the length, we'll be considering a factor called linear density, which is density mass divided by length. Mass per unit length is considered here. So each and every piece used to have the same density, but there will be different masses at different locations. So you can see that the negligible mass of him is a d theta, let's take it as rho dash, because rho is density, so rho dash is linear density. So this is going to actually give you the negligible mass. And be careful, okay? It's actually located at a certain distance. It's located at here. Let's say a distance x. So we know that by the principle of moment, the moment created by each individual pieces is equal to the resultant moment times its center of gravity. From that concept only we start getting this. So you should understand, we should know at what position it is actually present. So it is actually present at a distance here. So this entire thing is A, and the angle between that is theta. So it is A cos theta. Location of center of gravity of this is at a distance of A cos theta. So we can easily find it. The thing is A rho dash d theta times A cos theta will get you the moment created by him. And similar to this guy, there are infinite number of pieces. So we must integrate it divided by again the mass. A rho dash d theta integration. Now the limit of this has to be considered. You should understand the angle is actually moving from minus alpha to alpha. So actually you can see that it's symmetric alpha and alpha. So anything below the x-axis is minus. When you measure it in clockwise sense, it is positive. Sorry, negative. So this is actually minus and this is actually positive. So angle is actually moving from minus alpha onwards to positive alpha. Minus alpha onwards to alpha. So I think I just, when it comes to the hollow hemisphere center of gravity, we almost had a nature like this, but we were not moving from minus alpha to alpha because it was something like scooping a thing. So I said that we actually spraying a gun and we start rotating the hemisphere. So we don't move from minus alpha to alpha in that case. We only move from 0 to alpha. So if you had time, just check on that video. It will be given in the cards. So you can see that this will be my center of gravity's equation. And this uniform density can be cancelled off. So eventually we will be having A integration of minus alpha to alpha cos theta times d theta divided by d theta integrated from minus alpha onwards to alpha, which is my center of gravity. So you know the integration of cos theta is sin theta and the integration of 1 is theta. Whatever variable d theta means, it's theta. So we'll be having an answer around sin alpha over alpha into your radius. Because here you are getting a sin alpha. So sin theta. So whenever the limit is subjected, you're going to get sin alpha. 2 sin alpha actually. And here you'll be getting 2 alpha. It will cancel off and this will be the center of gravity of a uniform arc, not a sector. So in the next video, let's look at on how to find the center of gravity of a sector. And yeah, do subscribe on our channel and you can just go through our website, which is UR Academy, which is given in the description for further information.